it's too much. I mean, I did that last year, but it's a hassle to enter them. I have them posted on my grade sheets. I'll hand them back, and you'll have the exam scores. There's also, as far as issues with the exam, if you guys think you guys were wrong in any way for the points, you can come talk to me, or you can take the issue up with the TA, and it can get distributed to the proper channels. So basically, there are a couple problems I told him to be harsh on, and those were problems you guys have seen before, and there was just like, there's no way you could do anything but, like the last problem in the exam, the LRC circuit. I gave you that verbatim problem in the practice exam, and the answers are all like one-liners. So it's sort of like you either got it or you didn't for each of the parts. And there's one other problem which you guys have seen before. I told the TA to be not so lenient on. And also told them if dimensions are good, give a couple points. If the dimensions are wrong, but and if it's an obvious like oversight somewhere, you missed a square somewhere or something like that, take off a point or two. But if it's like completely just off, then no points. But other than that, I told them to just be consistent with whatever the grade they were doing. But yeah, if there are any issues, and there may as well be, because a lot of exams will take a lot of time, so there may be mistakes made in adding up, or points not given where they're deserved. Come talk to me or your TAs, and we'll rectify it as soon as we can. All right, you had a question?
Here on your lovely survey, it says course pace, and you graded it from too slow to too easy.
Oh, it's too slow to too fast, sorry. Yeah. I mean, I suppose it can be, if it's too fast, yeah. Fast may not necessarily be easy, but yeah, sorry, that's supposed to be too slow to too fast. So I mean, we're going for the Goldilocks on this one. So no, I don't want it to be too easy or too difficult, but just enough for you guys put in the time and learn something. So, right. So any other questions, or should we get started? Did everyone get a survey? There should be a survey. Yes, did you get one? There should be extras floating around. Can they make their way down somewhere? Up there. Right. So yeah, there should be extras floating around. So just please get one before. So when I hand the exams out, I'll take the survey from you, give your exam. Also, I asked for your name and email address on there. That's completely optional. If you'd like me to contact you about something that you want to discuss, then you can write your name and email address on there. But before I discuss anything with your TAs about the survey, I'll either cut that part out or tear it out. So it will be anonymous there. I'll be looking at them initially, and then once I take out all the names, then I'll give your TAs your respective survey so they can look at it too. But yeah, so it's completely optional, the names. You don't have to write your name or your email address on there. So yeah, so there'll be no chance of retribution in any form. All right, so let's get started with geometric optics. Now, throughout the course, I've been telling you guys this is quite a cut and dry, boring topic. And yesterday, when I was going through the notes I made for last year, I was, falling asleep, so it's pretty tired. And right about midnight, I had this moment of inspiration when I said, "Okay, I know how I can make this more interesting." So I spent the next few hours coming up with hopefully what is a more interesting lecture. So it went from me trying to not spend that much time in geometric optics to probably spending a lecture and a half or so on it. So hopefully you guys can take away some important stuff from this. So this topic is quite old. We'll actually be going back in time to cover this. And I mean it's old because we just finished up with the flurry of Maxwell's equations. Right? We went over Ampere's law, we went over Faraday's law, both the Gauss's laws before, and essentially what we concluded from Ampere and Faraday's law, was that we were able to come out with electromagnetic waves and their speed of travel, and basically that they can actually exist on their own and travel away from charges and currents. And then we also found or derived that they travel at a speed of light, which is 3 times 10 to the 8 meters per second. And it actually happened to be a coincidence that it happens to be that speed of light. And people conjectured for a while, quite accurately, that light was in fact an electromagnetic phenomenon. It was actually an oscillatory phenomenon. So it wasn't that the waves were just all modulating. It was that the strength of the electric field was oscillating down, and obviously was traveling through in time. And the field is basically, by what I mean by field, is it's a certain point that can be measured by putting a test charge. So when I say that the field is oscillating, it has a certain strength at a certain point. You can put a test charge and measure what the actual force is, and so on. So it's a condition in space that travels from source to some other place. Now, this point of view came near the end of the second half of the 19th century, and it came after many years of people studying light. So it wasn't an overnight discovery. And what I'm going to do today is tell you the different ways in which you can go away from this theory of light and of electromagnetic waves. One of the theories is when the wavelength is quite small. And something to think about is when I say something is small, it all is relative. I mean, if I'm looking at 1 meter, it may seem small, but if I say it has 1,000 millimeters, 1,000 millimeters seems like a bigger quantity. So it's all relative in terms of what your units are. So what I mean by my wavelength being small is it's really small compared to my scale of observation. And what I mean by that is I'll tell you in a minute. So if you're looking at a centimeter, if you're looking at the centimeter scale, let's say I'm looking at 10 to the negative 8 centimeters, that seems quite small, and it behaves. It's small enough where it behaves in a much simpler way, and we can at that point we can forget about waves and other stuff. And at that particular scale, we look at something called geometric optics, because what happens when you're looking at such a small scale is that you'll see light or rays traveling in a straight line. And from there we can say, okay, it travels in a straight line. We can do some geometry and trig with this, and then come up with what we see as geometric optics. It's basically from source to your eye. And if you take Maxwell's theory and apply it to this, then you'll get the approximation which I'll discuss today. So what I mean by small is if I were to take some source of light, and if I have some sort of a screen with a certain hole in it here, then if this hole is relatively big compared to the wavelength, so if this is like the diameter of this hole is d, then if I'm looking at the wavelength that's considerably smaller than that diameter, then if I put another screen over here, basically I'll see whatever is over here on this screen. If I put a little nudge over here, then I'll see that over there. So when I say the wavelength is small, it's small compared to the aperture, and in this case it's that hole of diameter d. And if another way to think about this is similar to what general relativity is to Newtonian mechanics. So Newtonian mechanics we know is good to a certain scale. Right? So if the particles are smaller than a speck of dust, or if they're larger than planets, then either special or general relativity will set in. And in principle, those things, when you apply it to the normal scale, will still work, but we can take an easier approximation, which we call Newtonian mechanics, and which you learn. You guys all had a lot of fun doing that. So in the same way, this is a similar case. When up to the scale where the lambda is approximately equal to the diameter, we can sort of work with, not to the scale. When it's smaller than the diameter, we can work with geometric optics. When it gets a lot bigger, something like that, then we need to go to something else. By that I mean that if the when lambda is approximately equal to the diameter, then if I have some screen, a small hole there, then what you would normally expect would happen is that if I have a light shining through, I'd get the normal rays that you would get there. But in fact, what would happen is you'd get more of a dispersion, and it wouldn't exactly follow a straight path. So that's where this sort of breaks down. And that sort of happens to be the limit of geometric optics. And Maxwell's theory isn't exactly perfect either. Sure, it may work for other cases here, but it doesn't work. It actually breaks down when you're looking at really low intensity of light. And again, we know from last time that intensity is proportional to either E squared or B squared, because obviously those two are related, they're proportional. If light becomes really dim, then you might think of E field, or the electric field, becoming smaller and smaller because the intensity is proportional to E squared. But something else happens when light becomes really weak, really dim. What happens is that, well, you realize that light is, the energy is not coming to you continuously. By that I mean, at this scale, you realize, okay, light's a wave, it's a continuous wave, it comes to you, that's fine. But then when it's really dim, you notice that it's not coming to you in a continuous form, and that's when we look at the particle side of it. We look at photons, right? And so that's when you'll have to look at quantum mechanics and look at discrete photons to come up with an explanation to fill at that scale. And it's similar to waterways and oceans and all that. So I mean, when you look at the ocean waves, you see, okay, more or less a general smooth form. But then if you go down to the microscopic level, you'll see that ocean or water is in fact made of separate discrete molecules. And if it just so happens that you're looking at small individual molecules, you can basically see that, okay, they still sort of follow that wave format, but it's coming in discrete levels. So it's similar to that. So what have we learned so far in terms of light and waves? Well, first off, we learned this. If I have some sort of a mirror here, let's say, and I have a light that's coming in here, it would go off in some other direction, right? And if I look at this axis here, and I call this angle theta 1, this is theta 2, basically means that theta 1 here equals theta 2. So the angle of incidence equals to angle of refraction, or reflection here. And we learned that. And then, from there, we said, okay, let's say I have some medium air here and some medium glass, and have some ray coming in. Obviously some of it would get reflected off, but then also some of it would get refracted. So it wouldn't go straight down, it would go at some certain angle here. Right? And then obviously there's some relationship. Let's call this theta 1, this will be theta 2, and let's call this some medium n1, some medium n2. And the relationship that Snell gave us was that n1 sine of theta 1 equals n2 sine of theta 2. Right, and then we all took that at face value. And then the speed at which light travels, is if we saw the speed of light. But then it wasn't exactly speed of light over here. Right? It's a fraction, some fraction of that. And we based that on index of refraction. And we said that the speed of light in some media was the speed of light in vacuum divided by the index of refraction n. And we're all happy with that, and we moved on. Most of you, I'm sure, have done the geometric optics stuff in high school to some extent. Just the simple ray diagrams, or at least most of you have seen it. Well, but for those of you that haven't, I'll do a quick overview, and we'll do some cool stuff with it. Or at least I think it's cool. So let's take a concave mirror. Here's my axis. And let's say I have a ray coming in, the parallel to the axis. This can get reflected, and go off over here, and we call this the focal point. And this is some sort of parabolic mirror. All right, and this also, of course, concave. So this ray comes in, it's parallel to the axis, and that's where it goes out, and we call that the focal point. So every parallel ray goes through a focal point. So you can use it to find the focus of that ray. And that's what you see when you have antennas, satellite dishes, and so on. You have some sort of parabolic dish. All the light, the parallel light comes in and basically gets reflected, goes to some certain focal point, and that's where you put your probe or receiver of some kind over there. And that from there you get the signal coming out. And so that's essentially how the satellites work. They focus all the light or the waves at one point, into one plane, in fact. So it's a property of these concave mirrors that they'll focus light at a certain focal point. So if I have more parallel rays coming in over here, if I have more parallel rays coming in, they will go through there, go through the focal point, and so on. And we can see if the rays come in from the bottom, they would also be more or less the same case as long as it's parallel. And it can actually become a mess. So we did that, and then we moved on to other stuff. And if you don't have an object at infinity, so right now we're thinking of rays coming in at a certain length infinity. Right? Now, if you don't have an object that's at infinity, then you're not exactly sending parallel rays all the way to a certain point. So, but rather you do some other something else to construct this. So coming from infinity, all the rays seem like they're parallel. They come in to that certain focal point. You find that to be the focus. So if I take a case where it's not at infinity, I would again, you guys may want to draw where your rays are coming from. So let's say I have an object here that's not at infinity, then you want to know where the image will be formed, and that will be sort of like we'll get there. So first thing you do again is you draw a parallel line. So this is my image. I draw my parallel line, goes through there, goes to the focal point, and goes somewhere down there, right? So this is my focal point. Now, the next thing you draw is a line through the focal point. So I draw my line through the focal point. It will hit the mirror, and it will go off at a certain point. And again, it's going this way, going that way, this way, this way. So this has some height h1. Over here at this point where those two intersect, that's where my image will be. This will have some height of h2. This length, let's say, is u. This length here for the image is somewhere, let's say, at v. So you get the image where these two rays would meet. Now, people have different convention of their own. They call those distances s prime, whatever it is, doesn't matter. Just, this is how I learned it, so that's, you guys can use that. So from here, you can get the result 1 over u plus 1 over v equals 1 over f, right? And this is essentially pretty much the only equation you know, and that's sort of what we have from those mirrors. And then, okay, we have different types of mirrors. Now we can move on to lenses. you guys still have recitation after this week? Not on Fridays, but after this week. Okay. So for your friends or whoever didn't show up today to pick up their exams, I'll hand them to their respective TAs so they can get them from recitation next time. So then, like I said, we come to lenses. Right, so we have a lens, a concave lens. Usually made some sort of piece of glass. I'm sure you guys have played with a lens like this at some point or another, either to burn ants or set brush on fire, whatever it is. So this has the property that when you shine parallel light from one side, all focuses on the other side. So if I have light coming in from this side, it's just coming in from some point infinity. Right, so I have light coming in. It all goes through, and it all focuses onto one point. Right, and we call that the focal point here. And the length here is the focal length. So if you have some object, it obeys the same equation again, except the distances mean different things here. So what u is here is that, let's say I have some object here, and that's where the light is coming from. So the distance from the object to the actual lens is u, and from the lens to where the where the image will form somewhere down here, that length is v. So you get the same equation, but the distances just mean something different here. So the still equation up there, 1 over u plus 1 over v equals 1 over f, holds. But the distance u is simply from the object to the lens. Distance v is the distance from the lens to the image. And then f is the focal length. Now, there can be some tricky situations that you can run into. For instance, if you have come across a convex lens, so some sort of a lens or a mirror here. Here's my plane. And if I were to look at some object over here, then let's say this parallel ray bounces it and goes off. So when the ray goes off into an abyss up there somewhere, it would seem like it came from down here somewhere. Now, if I draw something from here to over here and back down to basically to the center and back down, this ray would seem like it came from somewhere over there. And these two rays, they meet right there. And that, again, becomes my new focal point. And it also would be the point where, no, sorry, would this be the focal point? No, focal point would be, I think, over here. This is where the images would form. This is where the virtual image would form. So it's virtual because, well, it's not real. The image would form, I mean, it would seem like it forms there, so we call that a virtual image. So, in fact, the rays of this light in this mirror, instead of focusing at some point, all seem to behave like they came from the focal point. And the rays seem like it came from somewhere off to the other side. And when the parallel and the ray join, so where the parallel ray here and the ray over here join, that's where you would get the image. So this is a convex mirror, and this type of mirror you have in your cars. And this is the side view mirror where it has the message objects in mirror are closer than they appear. So that's a convex mirror. So if you should think of something like Jurassic Park here. You guys all have seen that movie, right? So I have some convex mirror here. I have dinosaur here, and ray comes in, goes off over there, and then I look at a ray coming to the center and then goes off somewhere over there, and then this would seem like it came from down there. This would seem like it came from up here. So the image I get over here, that's what the image of dinosaur would be. Reduced. So it's a smaller image, as you can even see by the height there. So it's a smaller image. Therefore, it forms a reduced image, so it seems like it's smaller, so it seems like it's farther away. And that's why you have the warning sign on the side view mirrors. So therefore, one of these mirrors, they'll make an image, but it's called a virtual image. So if you want to think about it, if you put a screen on the other side, you'd see like the image is on the other side. That's why it's called a virtual image. But then again, if you actually put a screen on the side, you won't actually see anything. So there won't actually be an image that forms over here, right? So it's virtual. So the difference between real and virtual, let me go through that. So if I take a concave mirror and I have a candle over here, right? So the image for the candle, the line goes in this way, comes out there. This is my focal point. Goes into the center. Sorry, it goes into the center here, but goes into the focal point. So it goes into the focal point and then comes out here somewhere. So this is my image that forms, and this is a real image. And this is my actual object. Now, in the case of the convex mirror, something like that, I have my object here, some candle. The ray would come in this way, bounce off there, come in this way, bounce off here. So what somewhere over here is where the virtual image would form. So it's not a real image, but we call this a virtual image. All right, so far so good. And in the case of convex mirror, for the calculations, you get the same formula. You get 1 over u plus 1 over v equals 1 over f, except f here is negative. Because it forms a virtual image, we said the focal length there is a negative value because it's on the other side. It's on the wrong side of the mirror, so it's a negative value. So now this is all pretty much cut and dry. It's boring. Now the interesting part comes from the actual derivations for this. So we can use, does anyone know how we can derive this? Everyone at all? No? So we can use something called Fermat's principle. This guy was a French mathematician, came up with a bunch of prime number stuff and all that. So we can use his principle to come up with this. Basically, it says that the light will go from start to finish in a path that takes the least amount of time. So it's the principle of least time. And that's what Fermat said. And us physicists, we like to derive a lot of pleasure in being able to derive a lot of things from a simple equation, simple formula, or simple principle. And that's precisely what we'll do. We'll be able to derive the three things we looked at today: Snell's law, the law of reflection, right? Angle of incidence equals angle of refraction, lenses stuff, and all those can be derived using Fermat's principle. Although lenses stuff, for this stuff, it takes a lot more math, so I won't be able to get to that today, but I'll start off the discussion for that, and then we'll end, and then Monday we'll pick it back up, finish it up real quick, and then start with even more interesting things. So the way this works is if I have 2 points, point over here, point over there, if I ask you, what's the fastest way to get from that point to that point? Straight line, right? It's simple. We've done this a lot of times before. It's as straight as I can draw it, but straight line, right? Straight line is the fastest. What's that? Someone say something? Never mind. Oh, okay. So straight line is obviously the fastest way there. So now if I had a mirror down here, so let me redraw this. So I have my 2 points, somewhere here, somewhere there, and I have a mirror down there. Now, I wanted to touch the mirror and then go to the second point. So if you want to think of it as one of those races that kids have, touch the wall and then run back to some other point. So it's something like that. So I want the ray to go from here to the mirror somewhere and then go to the second point over there. Slightly more complicated. I mean, I could in principle, obviously I can't go in a wiggly shape, right? Because if it's a race of touching the wall first, obviously you're not going to go zigzag, right? If you do that, you'll lose the race. So you want to go straight. So we know that it's some sort of a straight path, but what path is that? This thing can take the path of going down straight first, and then from there reflecting and going there, or going down here first and then going straight up. So we have many possibilities, many different straight lines that this thing can take in order to get to that point. Now, the path to the mirror again has to be straight, and then the path from the mirror has to be straight. We know that much. But what's the actual path? We don't know. So you have the freedom to choose whatever path you want. So instead of just stipulating and conjecturing about what the path can be, we can actually go through and derive what it should be. So I have my point here. So let's say that it takes some arbitrary path to down here and to up there. Let's call this D1 and D2. And let's say this here is H1, this here is H2. And the distance here between H1 and D1, or the point over here, is, let's say, X, where it's touching. And the whole length here is, let's say, length capital L. Now we can simply calculate what the minimum distance should be for it to be at an optimal level. Well, the way I want to do that, basically what I wanted to look at is the path it will take for it to travel in the least amount of time. So we're looking at time, and we're trying to optimize time here. Well, if I want to look at time, t, this is going to be equal to some distance d1 over the speed of light, right? It travels that distance at the speed of light, plus some distance d2 over the speed of light. Right? And let's say this is going to be equal to t is equal to d1. I know what it's going to be. If this is x, this is h1. Then d1 given by Pythagorean theorem is going to be simply h1 squared plus plus x squared, right? All over c. Plus, for the other one, it's going to be something similar. It's going to be h2 squared plus L minus x whole squared, right? Because this distance here is L minus x over c. And I can multiply both sides by c, so I get c times t equals that stuff. Now, you guys have all had differential calculus, right? So I believe that's a prerequisite for the class. So you guys all know how to take derivatives. You guys all know what the implication is when you take the first derivative, right? And you can take second derivative. So if you look at plots and their behaviors, if you take the first derivative set it equal to 0, you can find the minimum point. You take the second derivative, you can find points of inflection, all that good stuff rings a bell, right? Okay, so I want to minimize time. So what I can do is take the derivative of time and set it equal to 0. at which point I can find whatever condition I need to get the shortest amount of shortest distance, or optimize that. So therefore, when I take the derivative of this stuff here, I'd get x over square root of h1 squared plus x squared, right? I take the derivative of this, I get 1 over that whole stuff times 2x times the 1/2, so 1/2s cancel out, I get that, minus L minus x over square root of h2 squared plus L minus x squared. And I want to set this equal to 0. So I'll optimize my board space now. All right, so basically there has to be a point x that satisfies this condition, and that effectively boils down to this: x over d1 equals to L minus x over d2, right? I know that this is d1, this is d2. I bring this to the side and substitute that. Now these can also have angles here. So you can say that this is some mid-axis. Let's say this is angle of incidence, theta I. This is going to be angle of reflection, theta r. And the angles over here, let's say, are alpha and beta. Right? So I also know that theta I, the angle of incidence, is going to be equal to 90 minus alpha. Right? So this angle here is going to be the same thing as here, theta I. And by the same logic, I can say that theta r, the angle of reflection, is going to be 90 minus beta. And from this, or from over here, x over d1, that is effectively cosine of alpha. Yes? Now, this equals to L minus x over d, which is cosine of beta. Now, this basically means that alpha has to be equal to beta, which means that from there, 90 minus alpha equals to 90 minus beta, which means that theta I equals to theta r. Angle of incidence equals to angle of reflection. So using Fermat's principle of least time, we effectively showed that the angle of incidence, in fact, has to be the angle of reflection. Right, so far so good? Not lost? Any questions? Interesting stuff, right? More so than simply looking at ray diagrams for an hour and a half. All right, so it's quite interesting that, in fact, we got theta, angle of incidence equals angle of reflection this way for basically light to go from some point 1 to some point 2 after touching the mirror. And it has to do this in the least amount of time. That's basically a law of nature. And so we have our first victory with this principle of least time. So this reproduces the first part of Snell. Now let's look at the second part of Snell's law, where we look at refraction. So we need to look at what happens to light when it changes medium. So we're looking at, I have some boundary for medium here. This has some index of refraction n1, some index of refraction n2. I'm looking at some object here at height h1, right? And basically, I need the light to go down to over here at some point h2. Now, one possibility to go from there to there, as we looked at, is a straight line, right? So if I look at this, I can think, okay, why can't I do it in a straight line? But we want to spend, so if you think about it this way, let's say you're over here, you're a lifeguard at the beach, and over here is some damsel in distress asking you to come rescue her, or someone drowning, however you want to look at it. Now, you know that you can't, I mean, you can probably run pretty fast, but you can't swim as fast in water. You can't move through water as fast as you can in land, right? So when I'm looking at the principle of least time, I want to optimize it so that I spend just the right amount of time on land and just the right amount of time in water. I mean, in principle, I could run all the way over here and then go down, but I'm sure I'll cover more distance there, and I'm not sure that my speed in land is that much faster. I mean, you can even probably time this. You can time and see how fast you can run on land, and then see how fast you can swim through water, and then basically to come up with a proper ratio that will optimize it so that you spend just the right amount of time in water and just the right amount of time on land to get from where you are to where whoever's drowning is in right in time to save them, right? So that's pretty much what you want to do. So since we know, let's say this is some medium air, some medium water or glass, and we have light traveling through, we know that it travels at a fraction of the speed that it does in air or a vacuum. Because we know that the speed of light through some media is the speed of light over whatever the index of refraction may be for that media. And obviously we know that this is bigger than 1 for anything, right? Vacuum and air, more or less the same, and anything other than those, say some sort of dielectric media, it's larger than 1. So we know for a fact that speed of light through some media is slower. So again, we want to optimize this. So let's look at the case where instead of going through a straight line, I go through some farther distance and then take a different angle there. And let's say this angle, this distance here is x. Again, as usual, the whole length is L, and we want to optimize this now. So the time it takes, time t, is going to be equal to square root of h1 squared plus x squared over c. Now, the speed of light over here is c over n1, right? So it's some fraction of that speed. So I'll just rewrite this n1 on the top here, n1, plus h1 squared, h2 squared plus L minus x squared all over c times n2. Right, so far so good. Now we want to take the derivative of this. So if I take the derivative of this whole stuff and set it equal to 0, as we did last time, what we would get here is n1 x over square root of h1 squared plus x squared. This would equal to L minus x times n2 over square root of h2 squared plus L minus x quantity squared. And if I give this the same type of angle treatment I did last time, I would know that this is, well, I'm going to say this is some angle theta 1, this is going to be some angle theta 2, call this angle alpha, call this beta. So same thing we did last time, so this is going to be n1 cosine, it's going to be sine of whatever that angle is, plus that. So what I'll end up with essentially here, after I did the same thing I did last time, I'd get n1 sine of theta 1 equals n2 sine of theta 2. Just derived Snell's law. We can derive Snell's law with another principle. I mean, this may seem like a bit more math, but you can derive it using the wave formalism also. So it's also interesting to see that you get the same result approaching it with a few different paths. So this again has some interesting consequences when you go the other way around, as we discussed last time. So right now we're going from, let's say, air to water. But let's say you're going the other way around, you would go this way and you would refract in that way, and that's fine. But then let's say you're going from an index where n2 is larger than n1, then there's some critical angle which gives you total internal reflection. Right, so we discussed that last time. So this also has some interesting consequences. Now, whatever time we have left, we can look at the last one, which is all this race stuff. Now, we won't be able to finish the derivation for this or even start the proper derivation, but I'll set it up and I'll pose the right question for you guys to think about over the weekend, and on Monday, hopefully, we can finish that up. Let's start off with, well, essentially what you would call an ellipse. Actually, I'm going to need these lines over here. So let's say we want to take a path of least time here also. Now I have 2 points here equidistant from the center. Call these 2 points F. These 2 are essentially different focal points. Now let's say I have some sort of a barrier over here which light cannot travel through. So you know what, this is a better example would be, this is Texas, so I'm sure you guys all love your guns. So let's say, because we know that light photons, they can sort of behave like individual bullets. So I want to shoot a bullet, so some bad guys over here, I want to shoot a bullet from here to here. Let's say this surface over here, you can have perfect reflection. I can't shoot straight through. It's some sort of bulletproof double pane glass or something like that. So I can't shoot through. But so what would I do? Where can I shoot in order to kill him in the shortest amount of time? No, what movie was that? Wanted. Was it Jolie in there? Angelina Jolie? Yeah. I haven't seen that yet. Well, yeah, I suppose in principle we could bend physics. Why not, right? Since we're not talking in fantasy world, we can bend physics, therefore bend the path. But let's say we stick to the laws of physics here. This is a physics class. We're nothing if not lawful citizens, so let's stick to the laws of physics. So what would I do? Sure, but where do I shoot it? Okay. So you're saying that I can shoot it over here, and then it will come down over here, right? And that's also reasonable, and this would form sort of a similar triangle. It's the distance from here to here. From here to the middle is same to the distance from here to the middle. So by symmetry, it'll come out on the other side of the focal point, and that's a reasonable answer. Now, but I did mention this is like parabolic, so it's sort of an ellipse, and this has the 2 focal points. If I shoot the bullet anywhere in the ellipse, you guys may remember this from pre-calculus, maybe. No? You can shoot anywhere, so basically the ray can go anywhere, bounce off at any point. If I look at the tangent over here, it will bounce back and come to the other focal point. So I can basically shoot it anywhere. It will come to that focal point. So it turns out you can take more than one straight path, right? And you can basically point the gun anywhere, and then you can get to, yes? Yeah, but I mean, we're all physics students, so we know we're not that stupid. We're not going to shoot the bullet ourselves. Unless, of course, there's probably an exam coming up. You guys don't want to take the exam, and that possibility might seem pretty appealing. But it's not the first time. You know how many, when I was an undergrad, quite a few fire alarms in the physics building came up during exam times. So, but yeah. So that's the property of an ellipse. So if I take some ellipse, which is supposed to be like an ellipse, but I can't draw, so I'll leave it at that. It's focal point here, goes that way, so this is some distance r1, this is some distance r2. And we know the property of the ellipse is that r1 plus r2 equals constant. And the way, at least my pre-calculus teacher in 9th grade, that was 9th grade, yeah, demonstrated this to us was, I think he had a couple of either, no, one of those like thumbtacks or something like that that stuck on the board, had a piece of string, attached a marker to that. So basically attach it to that, and then you can draw around the whole ellipse from this. And that's effectively, these 2 points, those are the focal points. So that's the property of an ellipse. So in principle, r1 plus r2 is always going to be a constant. So I can go from here to here or anywhere else, and I'll get to the point in the same amount of distance. Right? So this, that's how focusing works here. And then it has to go from start to finish. And then if it has to go to the say other focal point, the distance will be the same no matter what path you choose. And this is how we make a focusing mirror, and they're all sort of parabolic. And that's sort of the best shape to use. I mean, everything uses a parabolic mirror. The Hubble telescope uses a parabolic mirror. So, and we'll also even discuss spherical mirrors, but so I have some axis there. I have some mirror over here. There's my axis. Let's say I have light all coming, from infinity. It's all coming in parallel lines, despite what my drawing looks like. Now, let's say I'm measuring the distance from. I have a cutoff. I measure the distance from there. So I would expect, let's say I draw a parallel line from there to here. It's going to bounce off, come over here, and this right here is my focal point. So this is some focal distance. So I know that it's going to take the same amount of distance. In principle, it could even travel out straight this way, but instead it will come down this way. So this distance here and this distance here will be the same. So basically, this is the focal length. I'm going to say this is also the focal length. But this whole thing is not the focal length. So basically, something like, well, yeah, this whole thing is focal length. There's some distance x over here that comes down. So the time of travel has to be the same for all different rays. So even if I were to come in at some angle, it would have to go through. So basically, the distance I would travel over here. So if I make a line from there, it could travel out this way, but it would go down this way. So this distance here, you can see, is longer than that distance. But yeah, so the overall travel time has to be the same. And any point on that curve has to be the same distance. So if we were to take, let's say, some arbitrary point over here as a function of x and y, I can get this parabola as a function of y of x, right? So I can try to find the function that would make it so that I can construct a mirror that will focus properly. So if I were to look at that, I mean, I can look at a couple of different things, right? So if I look at this distance here, basically I have some length over here, something like this. So over here I have x plus f, and so I'm looking at some triangle there, so I can say that x plus f has to be equal to the other path. So x plus f has to be equal to the square root of y squared plus f minus x whole squared. So I can, I believe this whole thing has to be squared also. Yeah. No, yeah, so look at this, but I want to get rid of the square root, so I square both sides. So when I square this part out, I would get x squared plus f squared plus 2fx equals 2 y squared plus square the inside over there out, so I get f squared plus x squared minus 2fx. So the x squares would cancel out, f squares cancel out, so I get 2fx plus equals y squared minus 2fx. So what I would end up getting here is that y squared equals 4fx Is this y squared? Yeah. So that's my equation for the parabola. So I mean, this may not be used to what you're looking at. Usually you're used to looking at a parabola like this. Basically, this is shifted on the axis, so you'd get something like this. So I'm sure you guys are familiar with the square root function. You look at something like this. It's basically plus or minus of that function, so you get something on both sides. So it's just sort of a shifted parabola. Now, to construct elliptical mirrors or parabolic mirrors is actually quite expensive because it's quite difficult to machine something to that precision where you'd get proper focusing. So a cheap trick that you can use if you want to construct a mirror on the cheap is to look at a sphere. So now, if we look at a spherical mirror, it's not going to be quite the same, but we can make some valuable approximations that will allow us to get the result we want. So what we can do here is have some parabola. If I take a sphere of a certain radius r and put it in here, there's going to be a certain point over here, so like maybe somewhere over here, that beyond this point, the sphere and the parabola are pretty much identical. But from here on out, you can see that the sphere and parabola, they diverge. So as long as we're looking at this small distance, we can construct a spherical mirror and essentially get away with it. So it imitates to a certain extent what a parabolic mirror should be like, and then from there it deviates. So we're looking at a certain sphere of radius r, right? And obviously this is radius there. So now if I wanted to look at what the equation is for that sphere, it would look like something like this. I would have x minus r squared plus y squared equals r squared. So I squared that part out, so I would get x squared plus r squared minus 2rx plus y squared equals r squared. So from here I can deduce, cancel out the r squared. Y squared is in fact 2xr minus x squared. So except for this minus term, we see a minus x squared term here, it's pretty much identical to what we got with the board up there. Now, right? We got the equation over there, y squared equals 4 xf, f being the focal length. So because I'm saying over here it imitates it, so because I'm going to say that this x squared is pretty small. The order in which it goes is u, v, and f are big. The lengths are quite large. Y is small, and then x is also even smaller, so you can say it's small squared. Right? So if I'm looking at something small squared, then in principle, since we're looking at approximations here anyways, we can ignore that term. So what I can do now is I can equate that equation over here, equate the y squared, so I get 4xf is equal to 2xr. So x cancel out, so what I end up getting here is that f equals to r over 2, or r is 2 times the focal length. Write that down too. So again, I can ignore that minus x squared term because I'm looking at an approximation to begin with, a small length here. So if you take a spherical mirror like this, and I have, let me get another board. So if I take a spherical mirror here, I have some object over here shining light, so I would get something like this. It would go through, reflect, go off at some point. We call this the focal point, and this focal point is half the distance of the radius. So if I were to look at that, this going to be somewhere in the arc. Now, again, we know that this has to follow that first equation we derived, so we know that the angle of incident here has to be the angle of reflection. I has to be equal to r. So let's look at the geometry for this and show it to you again. So I think like fourth or fifth time I'm showing that the angle of incident has to be equal to the angle of reflection. So let's draw a bigger image, so you guys can see in the back. All right, so here's something there. So I have some ray coming in, go through with the focal point here, F. But if I look at that point here, if I look at the tangent for that point, right, I can see that this is at some point R. So I'm going to say this is angle A, this is angle B. So if this is B, you know that this is A, and this has to be equal to B there. And I'm going to take this height to be some height h. Now, the tangent of B is equal to h over f. Right? So this is a focal. I mean, it's supposed to be not exactly. Now I'm looking at this distance here, but I ignored that x squared term. Yes.
On your angle B on the lower, is that not equal to B plus A?
Over here.
That term right there, is that not B plus A?
This term over here, would it be B plus A? No. Wait, no, it's not going to be B plus A. This is going to be simply B.
You have the top and the bottom are parallel. So if the top line and the bottom line are parallel, and then you have a line dissecting, it should be alternating interior angles. So it should be B plus A.
Okay, well. I believe this is B, but then this angle would change over there. Yeah, it seems to be a logical explanation for that. Okay, yeah, you're right. So it has to be B plus A here. Yeah. H over. Not quite. Well, we know the tangent of A, if I take that to be A, it's going to be H over R. So that's, okay, yeah, I think you're right there. This is tangent of A plus B. It's going to be H over F. right? So, but now I can take the small angle approximation. With this, you guys are all familiar with that, right? So I can say for really small angles, sine of theta is approximately theta. Cosine of theta is approximately 1, which means that tangent of theta is approximately theta. So I can say here that a plus b equals to h over f, and then a equals h over r. And we know that f is 2r, right? No, r is 2f. So from there I can say that a equals to h over 2f, which means that a is going to be equal to that's 2f, then it's going to be equal to b over 2. Wait, I think this is what I did in my notes. Sorry. So I'm saying that this whole angle is b. That's the angle over there is a. So this means that this whole thing is b. Yeah. Sorry, I misread my notes. There. That should fix it. Yeah, in principle, if I had a and b separated out, it would be, you're right. But so this whole angle is b and that whole angle is b, so which means that this is a, this is a, which means that this whole thing is going to be, this whole thing over here is going to be 2a. Right? So, yeah, because now it's, sum of exterior angles, that has to be 2a. So we know that this whole thing is 2a, this is a, we know that this has to be equal to a. And again, this only works for small angles, which is fine because we're taking an approximation to begin with, and we also skipped some of the steps in there. So small angle here means that your object is not too tall. It can be too tall compared to the radius of the sphere. So that's when you get the small angle approximations. Otherwise, this approximation is no longer valid, and you can't really use spherical mirrors here. So we showed that these two are equal. Now let's go back and look at and see if we can derive the focal points and all that. All right, so if I look at spherical mirror again, here's my axis. I'm looking at some object of height h1, which means that I would get a ray going in. So let's look at my parallel one. I draw my parallel ray, comes in here, reflects off, goes down there. And now I'll look at the other one where I'm looking at things coming to the middle and then going over here and then bouncing back over here. So I'll give these same angle treatment as I did for the other ones. This will be beta, this will be alpha. Over here, whatever this height is, I'll call that h2. That's alpha, then this is going to be alpha, this is going to be beta. So over here, this is also going to be h2. This whole distance up to here is u. This whole distance here is v. This is my focal point f. So using the same principles as last time, I can say that my tangent of alpha over here is h1 over u minus f. Right? So tangent of alpha equals to h1 over u minus f. And this again equals to h2 over f. Equals to h2 over f. Tangent of beta equals to, well, I have beta here. This equals to, well, this is going to be some height h1 over u, or sorry, h1 over f. and this is also going to be equal to h2 over u minus f. Right? So it's actually, technically it's not exactly f here, right? You know, we're looking at some, this whole thing is f, then I have some distance x here. So in principle, this can be some distance f minus x, but making the same approximation I did before, I'm saying x is really small, so I'm going to ignore that. So I can ignore that because of our approximation, and from this, we can get all the stuff that that's given by these two rays. So what I'm going to do now is I'm going to cross multiply these terms. I have these two. I'll cross multiply these two. So what I will end up getting now is h1, h2 over u minus f, oh sorry, that's going to be a v, it's supposed to be a v. You guys can correct me, this length is v, so this is going to be v here. So it's going to be v minus f here. And again, this is going to be equal to the other one, h1, h2 over f squared. So these two, the numerators are the same, so I can write this as u minus f times v minus f equals f squared. I can invert and cross out the h1, h2. If I multiply this out, remove the parentheses, I get uv minus uf minus vf plus f squared equals to f squared. So I can cancel out the f squares here, and from here, and also I'll divide both sides by u, v, and f. So from here, what I'll end up getting is 1 over v plus 1 over u equals 1 over f. This is not derived through Fermat's principle of least time, but rather I derived this using geometric optics, and there are basically basic geometry. So we had two equations here, and we only got one answer here. So we can find something else out that can be meaningful from this. So the question we can ask ourselves is, what's the ratio between the object size and the image size? Well, I can look at h1 over h2. This is going to be equal to f over u minus f. So this is going to be this is h2 over h1. I can also write this as h1 over h2, which is going to be u minus f over f. This is going to be u over f minus 1. Right, so this is going to be, I can factor out the u, so I get u times 1 over u plus 1 over v, right, because I know what the 1 over f is. I'm basically multiplying it by with that. Minus 1 equals u over v. So the ratio of the object size to image size is the ratio of the object distance to the image distance. And we define this as magnification, and magnification m equals to negative u over v. And what we mean by the negative is, if this thing comes out as negative, then it means that the image is upside down from the object. Right? So our object is pointing straight up, then our image that we look at is pointing down. And if that image comes out to be positive, then it's upright. Now we looked at two rays for that. So one of the rays goes parallel, goes to a focal point. Another one goes through the focal point, hits the other end, and then bounces back parallel. Now what happens if we add a third ray? Right, so let me tell you what I mean by that. So what I mean by looking at a third ray is if I have my mirror here and I have some object height h1, and we look at the standard ones. Instead of going to some standard location, it's going down to some point y, height y away, and then bounces back. And if you want to look at it, it comes out somewhere. These two bounce meet over here. So this is where I get my h2. This is u. This is v. Now, that's the third one. I mean, I could have other rays hitting, at some other angle, but it still has to meet at that particular point. So how do we come that up? And basically what I'm asking you here is, here it's h1 squared plus u squared plus square root of h2 squared plus v squared equals some distance d1 plus d2, where this length is d1, this length is d2. Right? Again, so basically these distances d1 and d2 are a function of y. So if I'm looking at the y where it's 0, so what I'm looking at, if it's a function of y, the distance is d1 of y plus d2 of y. They have to be equal to d1 at y0 plus d2 at y being 0. So I want to equate these two, and that's what I basically mean by this. It's going to require a lot more math, but hopefully I can find time to finish it up on Monday. Hopefully this was a lot more interesting than just looking at a bunch of ray diagrams all day. All right, so the way I'm going to divide this up is, give me just a second. Let me stop this.